Welcome to my first video for CSC148. I'm Michael Miljanovic. If you don't know me, I am one of the coordinators for the course and the instructor of the first lecture session. And I'm looking forward to recording a bunch of these videos which are going to go over the course notes. You don't have to watch these videos, but if you find that you learn a little bit better from listening to somebody talking about stuff, then maybe these videos are a good supplement for you as opposed to just reading the course notes, which I'm going to go through in this video series. Before we jump into all the stuff for 148, we are going to review a little bit of stuff that you should know, I believe, from CSC108, which is going to cover parts 1.1 all the way up through 1.7 of the course notes. So without further ado, let's go on through it. First off, we're going to talk about data. So data in Python pretty much has three main components: an identifier, the type of the data, and the value of the data. Usually we only really care mostly about the last of these because we can typically infer the second one, and the first one we personally usually don't need to know, but that doesn't mean that these aren't actually present, and in particular the computer obviously needs to know all of these things in order for it to work. So the identifier, the ID of an object, is a unique number that specifies a specific object. No other object is going to have that number, and usually this is something like the memory address being the same as the ID, but it doesn't have to be necessarily the same thing. The only thing that matters for ID is that it always only ever refers to one thing. If you want to see what the ID of anything is, you can just call the ID function. So there's a couple examples here. I'll pop over here and do it. Can I zoom in on this a little bit? There, I zoomed in pretty far, but that's okay. So if we said, the ID of the number 5, it gives us this value. We can do ID 3 like it has in the example, and it gives, notice the number is like only slightly different from here. Later on you'll learn exactly how different this number is from this number. But one thing that you might notice right away is that when I do ID 3, I get a number here that's not necessarily the same as the one that's here on the slides. And this really just depends from computer to computer. You might be able to run this and get a completely different number than I do as well. Now, in addition to ID, we can look at the type of an object by calling the type function. So kind of unsurprising, if I want to know what the type of 3 is, well, it's an integer. The type of the letter C is string. The type of 5.5 is a floating point number, for example. All the different kinds of types of anything you can think of, you can just call this highlighted in purple in my IDE function, and it will tell you what type that object has. Type is important because it determines what kind of operations you can use. For example, you can round an integer or a floating point number, but you can't round a string. That wouldn't make sense. How do you round the word Michael? What are you going to round to? I'm a little scared. But if I call round of 5.5, it'll round up to 6. Round of 5.4 rounds back down to 5. Round of just an integer will just give me the integer. But if I try to do round of my name, oh no, you can't do that because string objects don't have a definition for what round is, so you just straight up can't do it. Now, type is also going to affect the built-in operators that Python has: plus, multiply, so on and so forth. So something like plus can allow you to add two numbers together, or even add two strings together, but you can't add a string and an integer together. How's that going to work? So if I have Michael plus my last name with a little space there, it gives me my full name. If I do 5 plus 6 gives me 11. Now here's a neat one. So obviously if I do 5 plus my name, it's probably going to be confused. What unsupported operand type? Because it doesn't know how to add two of these things together. One thing I can do though is I can do Michael times 2. Oh, it actually doubles my name. So not always the case that it's impossible to run some of these operations on different typed objects, but sometimes the behavior is just not defined. There isn't some way to explain what it means to add 5 to Michael. And now, of course, there are some ways that you can, add 5 as a character to my name and get, 5 Michael. But that's something we'll talk about later. So I've already really showed this, but anytime that you're working with the terminal, which is what I have here, this is just running one line of Python code at a time. I'm not actually writing a whole program here, just doing a single Python execution. Anytime you enter any just straight object reference or anything in here, you will just get the value. So if I just type 8 or 3.5, it just directly evaluates and tells me what the value of the thing is, which is most of the time what you want. So let's start talking a little bit about variables. All languages that I can think of in programming have the concept of variables, and in Python, a variable is not an object, but rather is the identifier of an object that stores the data you're looking at. It's a little bit convoluted, but you can usually think of it as the case of this name refers to where this value is stored. So here's some code here, and I've transferred it directly over to good old Python tutor, which is just going to run these one at a time and show you exactly what memory is looking like as we execute these lines of code. So when I run x equals 3, what happens here is we now have a global variable, global because I'm not putting this in a function or anything, which we will call x, and x has is associated with the value 3 because there's an object that has 3 there, and if I go and print out x, it will print out 3. If I try to print the type of x, it's an integer because it's got the 3 there, and the ID of x is this thing. Similarly, if I assign a word to be bonjour, and I print the type out, it's a string. If I print the ID out, it's this number. And now, curiously, if I do the following, print ID of 3 over here, you'll see that in this case what I've done is printed out the ID of both 3 and x, and they are the exact same thing. Meaning that any time that I'm referring to x, what I'm really referring to is just where the computer sees the number 3. So that way these refer to the exact same thing, which is probably what you want if you want to be able to refer to x and get the value 3 out of it. So in the notes here, you'll see the little state of memory, which kind of matches what we have going on here at the very end, where we have x associated with 3, word associated with bonjour, and in here we have like a little bit of an extra step here, where really it's the object, which is 3 in the top right there, has an ID, which is the exact same as the ID that we get out of x. And similarly, we have the ID for bonjour and word, which are the same. And so the value of these, we never really care about. All that we need to know is that each of these objects has a unique identifier, so you can make sure that anytime you are talking about x, you are talking about 3. Anytime I'm talking about 3, it is the 3, the only 3 that exists. And now you'll see in here that x and 3 are like kind of separated by this bar, and similarly in this diagram, x and 3 are like completely separate. That's because x refers to 3. We wouldn't say that x is 3, because x is a variable, and it could change for all we know, right? The value that's associated with x, we could make it 5 later, right? So x isn't just always going to be 3, but in this case, it refers to 3, so that we make sure right now, if we need to go and pick it up, the value that we're going to get is the 3 that we want. This probably sounds like I'm talking in circles, but the important thing here is just to understand what it means when I say refers to. In this case, we're talking about having the unique identifier that says, if you're going to x, that means you're going to go see a 3, or x references. So a couple of things to notice. Since we didn't write what a string is in Python, it's kind of already there. We don't know anything about data used to store the contents, so that's why we're writing bonjour in this box, which is perfectly fine. But in reality, the computer might represent this in a little bit of a different way. Also, there are no arrows in here. It may be to your benefit if you're trying to figure out what a program is doing to draw some of these arrows in. And I'll probably have some later videos that do include some arrows to help follow along a little bit with where numbers are coming from. And once you're really confident with a language and you want to know how your references work, you can have all these arrows going. But right now you might want to, just to be super clear that you understand what's going on, to actually write down like ID whatever if you want to. So the whole power of a variable is the fact that you can change its value, right? Pop open here, can have my cat named Gilbert, and when I say cat, it says Gilbert, and when I do the ID of cat, it says this. Alternatively, I can have my cat be Rupa. Now cat refers to Rupa. The ID of cat, you see, now has changed from here to here. And so in this example, there is only one variable named cat. At first, it has the ID of this string. Later, it changes to be a different string ID. These are pretty simple, but it's really worth making sure that you can understand why these IDs have changed when I've reassigned the value. And later on, when we start doing a little bit more debugging, it's pretty important to realize how to distinguish between some of these changes. But more on that, I think, when we get there. Now, something very important is that objects have a type and variables don't. So when we did type of word, we got string, right? If I do type of cat right now, cat, it's also a string. However, it's perfectly valid for me to just decide right now, you know what, cat's 5 now. And what is the type of cat? Now it's an integer. I've changed it. So this basically means that variables in general never are going to be restricted to a single type in Python. Other languages do not have this same feature. Something like Java, if something's going to have an integer, it's always going to refer to an integer. It's never going to be something different. Python is not like that. Python, you can just be like, you know what, word is edu, or word is 42, and these are all perfectly valid Python, and it will work even if you think it's kind of silly that it does. So if you're taking 148, then you've either done enough Python on your own or taken 108 and written code far more complex than what I've been talking about so far. But you probably haven't had to think in little details about exactly what goes into every expression or statement that you write down. Even something as simple as an assignment. And so in order to learn in what we do in 148, you're going to want to know exactly what's happening step by step in order so that you don't make any mistakes about what's actually going on in the computer. So what happens when Python runs an assignment statement? So assignment statement is something like, cat equals 10, right? Okay, what's the order of things that happen? Well, first off, we look at what's on the right-hand side. That gives us the ID of an object. So here it's pretty simple. The right-hand side is 10. But if I decided to do, cat is 10 plus 5, the order in which things are happen is the very first thing is 10 plus 5 is evaluated and considered to be 15, and we get that ID of that object. If the variable on the left-hand side doesn't already exist, we create it. If it does exist, then, it's already there. So we just have to, we can just sit, we're okay. We then take the ID that we've generated on the right-hand side and store it in the variable on the left-hand side. So now if I do the ID of 15 and the ID of cat, they are the same. Now, any assignment statement in Python always has an expression on the right-hand side, without exception. Expressions can occur in other places also, for instance, in a function call. Anytime an expression is encountered, we have to evaluate it. So this always gives you a value, which is the ID of the object. And so here's what Python does. If the expression is a variable, so it's cat, you go find the variable. If the variable doesn't exist, then you have an error. If it does exist, the value of the expression is the ID stored in that variable. If the expression is what we call a literal value, so this is something like straight up the number 176.4 or the word hello, create an object of the appropriate type to hold that value. The value of the expression is the ID of that object. If the expression is an operator, like plus or modulo, evaluate the operands, the two things that are on either side, apply the operator to them, and create a new object that holds the result. and the value of the expression is the ID of that object. There are other rules, but this is sort of the like nuts and bolts, most important part. So let's give a quick example of this working, right? So one function you can consider is round. So I could do round of cat plus 6. Okay, and so what's going to happen in here? Let's go through our steps again. The expression has a variable in it, so we're going to need to find that variable. If it doesn't exist, there's an error. So let's cause an error right now just for fun. We're going to check for a bat. All right, let's go. Oh no, but bat's not defined because the variable is missing, right? Okay, let's try this again. So the expression here we have is a variable. So we go find it. We find cat, and cat has this ID. Great, okay. Then on the other side, we have a literal value. So this is like the number 6. We make an object that is going to hold 6, and we get the ID of that. And now we have actually an operator here. We have plus. So we evaluate the two operands. In other words, we figure out what to do with cat, figure out what to do with 6. We then apply the addition to them and create a new object of the appropriate type, and the value of the expression is the ID of that object. So when we run this, we get, hooray, 21. So if we did ID of this, we get this, which is the same as the ID of 21. Okay, let's talk about mutability. So some data types in Python, some examples include integers, strings, booleans are immutable. And what this means is that the value stored in an object of that type cannot be changed. Here's some sample code. And so, let's give our own little analogy here. Prof is me. And the ID of the prof is this. Okay, cool. Let's make that be myself plus my last name, just for fun. Prof I get is this. Now, the old string object can't change, so Python makes a new one. Since it's new, the ID is now different. So if I do the ID of prof, you can see that this ID and this ID are not the same. So what actually happened here in our code? Well, here's kind of an example of it. When we first set up that prof referred to me or Diane, there is an object there that stores the value of Diane. And so at first, we have ID 8 here, meaning that prof refers to that original Diane initially. Then we need to change things. We need to now go and say, hey, we're actually looking to refer to Diane Horton? Horton, yes. Instead. So our original Diane doesn't just disappear. That's still there. But we're going to change where prof refers to. Instead of referring to Diane, it's now going to refer to Diane Horton, the whole name. In here, you can see that the boxes on the right are double outlined. This basically means immutable. So you can't just go there and change the values that are in there. So in this example, we reassigned the variable prof. We made it refer to a new object. And we can do this even though strings themselves are immutable. Regardless of whether a object is mutable or not, you can always reassign a variable. Now, that's what it means to be immutable. What about being mutable? Well, more complex data structures in Python, things like lists or your classes or dictionaries, all are mutable. They can be changed. So let's take an example of this list. So here we got x is 1, 2, 3. So 1, 2, 3. Here we'll make our own on the side just for fun. So my list is, we're gonna go 4, 5, 6 because we're gonna one up ourselves. And if I type my list, 4, 5, 6. What's the type of my list? It is a list. What's the ID of my list? It's got some number. Okay, now let's change things up, right? We're going to change the first number of our list, and then we're going to add stuff to the end of it. So we got my list, and we're going to set my list's first element at index 0 to be 400. And now let's see what happens. So my list is now 40056. What's the ID of my list? Interesting. Before, when we changed our variables, the IDs also changed. Here the ID has not changed. It stayed the same. What if I extend my list? I'll do my list dot extend, and we're gonna add some stuff onto it, 100, 200, 300, just for fun. What's my list now? Well, it's got lots of values in it. What's the ID of my list? Still the exact same thing. No matter what we're doing to change this list, the ID of my list still stays exactly as it was when I first set it up. So here's a look at what's going on in memory. I guess we can actually, we can probably pull on this over here as well. So we'll do my list is, 1, 2, 3, or here, 4, 5, 6. My list 0 is 4,000. My list dot extend 100, 200, 300. We did 400 actually, not 4,000. Let's just see what happens every step of the way, right? So, okay. Here's where our arrows come in real handy, right? So my list here is just a variable that refers to a list, and the list has a bunch of different values in here. In the list, we have indices 0, 1, and 2. Each index refers to a different object inside of it. So we have the 4 here, the 5 here, the 6 here. And my list is literally just a reference to where that list is in the memory. So when I do my list 0 is 400, we're going to go in and change this 4 to be 400, but the arrow didn't change. The arrow is still exactly as it was before. And inside my list, now obviously the first element is going to now refer to 400 instead of to 4, but my list itself is still in the same spot that it was before. When we do extend, the exact same thing. Our list gets bigger, but my list is still referring to the same spot as it was. So here's, the MS Paint version of that same thing. X over here is the list, and we can see, here, let me open this in a new tab. So this is the list itself, X, and X is referring to our list of all the objects, and we can change what's in this list all we want. We can add some new stuff to it. In green here we added new things. We can replace what's there before. Now, the actual number 1 itself, or 4 or 5 or 6, are immutable. They cannot be changed. And so these all are kind of stuck there and can't be moved. But you can create new objects. Here we got a 10 now, a 20, a 30, a 1 million, a 400, and change what's actually in these boxes to instead refer to different objects. And that's kind of what we're doing every time we're manipulating a list. So the reason that we use the term immutable or mutable is because the lines that we ran where we reassigned one of the elements or where we extended the list mutate the object. They take the object exactly as it was before and they change it, but they don't refer to new ones. We're not generating a new list every time that we add an element or move an element or something like that. Now, aliasing is when two variables refer to the same object. We say that those variables are aliases of each other. So here, here's some code of x, y, and z. X is a 1, 2, 3. Y is a 1, 2, 3. And z is x. Because z is x, they are aliases. They refer to the same thing. So here, let's try that out, right? We're gonna once again one up ourselves just for fun. 4, 5, 6. Y is also 4, 5, 6. Here, we'll make them look exactly equal just for fun. And z is x. Okay, so now the ID of x is this. The ID of z is also that. The ID of y is something different. Y and x even though they originally start out with the same list that I initialized them with, they are not referring to the same thing. And we can see it over here as well, actually. Let's do the same thing. X is 456, Y is 456, Z is X. Let's see exactly what happens with these lines. So X, new list. Y, a different list. Z, look at these. They're pointing at the same spot because they're referring to the same thing, which means when I make changes to Z or X, the alias variable also sees those changes. So, let's go Z of 2 is 600. So this 600 now means that X is also going to have the list 4, 5, 600, even though I changed Z, because they're referring to the same thing. But Y was not touched at all because it's completely different. So here's another MS Paint version of our memory. X, Y, and Z, and you can see these two are referring to the same thing. In my little arrows example, they're both pointing to the same spot. So yeah, Z refers to the same object that X refers to. So here is the list that's X and Z, which means if we change these, they both notice the change. And here is the list of Y, which is a completely different list altogether. So aliasing, you can see, can cause a lot of confusion because it allows you to change things somewhat indirectly, right? And I guess I jumped the gun a bit by showing this exact example, but if I do X is 1, 2, 3, Z is X, and I change Z 0, what happens to X? Well, let's do it, right? Copy, paste. We'll delete these arrows, and we'll print out X for fun. So here's my list. Z now refers to the same thing. Z of 0 becomes negative 999, so this becomes negative 999. When I print out X, it prints out this list that they're both pointing to. So we call this a side effect because it's specifically a case where we are mutating the value of a variable, which then affects an alias of that variable. And this can be confusing because it leads to a lot of misunderstandings. So, you can say the third line mutates the value of Z. To be more precise, the third line mutates the object that Z is referring to. Because, Z's value doesn't actually change because Z is actually just referring to a list. And, here's another MS Paint version of that, right? When we make the change to set our number to be negative 999, all we really have done is we've gone into our list and we just changed that one number there. We didn't actually change Z or X themselves. They still have the same ID / the same arrow associated with them. So the reason that this is tricky is because when you're just looking at the line of code by itself, Z of 0 is negative 999, you wouldn't know from this right away that X has changed too. You would have to know that Z and X are aliases, and thus any change to one will affect the other one. So, here's comparative code. Let's see what happens with this one. We're just gonna run it again, right? Big, really helpful lesson for this course. If you're ever unsure about what code is doing, just run it. Just try it out and then see what happens. And that can answer a lot of your questions about, well, what's this gonna do? Give it a try. So, okay, here's some code. Let's see what happens, right? We'll print this. Okay. X is this list. Cool. Y is this list. Cool. We're going to change Y's 0th element to be negative 999. Zoop. This one changed. This one did not. And so when I print X, nothing has changed. Everything is still all great. So, why is that the case? Well, because the third line mutates the object that Y is referring to, but that's a different object than the one X is referring to. Here's our MS Paint diagram again, but hopefully I trust that you've been following along okay. Now, aliasing also exists for immutable data. But in this case, you can't have this quote-unquote action at a distance thing happening because immutable values can't change. So an example of this is a tuple. A tuple is kind of like a list, but it's immutable. So here's an example here where we have the exact same thing basically, except instead of a list, we have a tuple. And let's see what happens when we try to do this. Here, we'll do it here. X is 1, 2, 3. Z equals X. And now we'll try to change Z0 to be, minus 999. Oh, you can't, because you can't change a tuple because a tuple is immutable, unlike a list. Now, changing a reference and mutating a value don't mean the same thing. So here's another example, right? What happens if we did this instead? Before reading on, let's try it, right? Okay, X is 1, 2, 3. Z is X. Now let's say Z is 1, 2, 3, 40. Pause for a second here. What do you think X is going to be? Think about it. Pause the video and then return. Okay. It's still 1, 2, 3, right? Why is this? X and Z at first are referring to the same thing. They're both referring to 1, 2, 3. When we change Z on this line, X doesn't change too. It's an emphatic no, and this is because of what kind of change we're doing here. We're not mutating the object by making some alteration to it. We're just deciding, you know what? Z doesn't refer to this tuple anymore. Z now refers to this tuple. They are two different things. So after this, Z and X are no longer aliases of one another. In general, a statement of this form, variable equals blank, never mutates the object that the variable is referring to. All it ever does is set the variable to refer to some different object. Keep this in mind anytime you're writing your code, because it's often confusing when you're trying to mutate values / change references. Now, sometimes it makes sense to make a copy of data so that you can change it without affecting the original one. Now, sometimes this is not a great thing to do. If you can avoid it, you usually should, because it takes both space, you're now using double the space, and it takes time as well, so it's sometimes unnecessary. So there's two different types of equality that we're going to look at, and let's look at this code here, right? What if we wanted to see if X and Y were the same, right? Well, what do we mean by the same? Let's try it out. I'm probably skipping a little bit ahead, but you know what? It's fine. So X is 1, 2, 3. Y is 1, 2, 3. And so now here's our question. Are X and Y equal? Well, what happens if I do X equals Y? True. So X and Y are true. And if I set another variable Z to be X equals Z, also true, right? Alternatively, we can use the is operator to compare the IDs of the objects they reference. So with is, we're asking, do two variables refer to the same exact object? And this is called identity equality. So let's try this. X is Y. Not true. X is Z. They are true. All built-in types have some implementation for this double equals, which allows you to check, are the values the same? But this isn't the same as, are the IDs equal? Because again, if I look at the IDs of ID of X, ID of Z, same. ID of Y, not the same. And so this is something that you're checking with is instead of double equals. So these don't mean exactly the same thing. Understanding the difference is a very important thing to take away from this video. Now, with immutable objects, things work a little differently. Because integers are immutable, there's not a lot of point in Python making a separate int object every time you need to refer to a number, like 0 or such. They can all refer to the same object, and nothing really bad can happen with any aliases because the object itself can never change. So here's some code down below. X is 43, Y is 43, Z is X. With our previous example with the list, we would have one object that's this list, one object that's this list. But because 43 can't ever be a different value, you can't just someday wake up and decide, you know what, 43 now means 7. Like, that doesn't ever happen. Because of that, they all are going to reference the exact same integer object, which is the 43. Whether or not they are the same integer object doesn't matter to double equals, so x and y, they have the same value, 43. But does check, are they referencing the same object? We wouldn't expect them, based on our previous example, to refer to the same object. But we know that Python likes to shortcut things and doesn't decide to create a second integer object holding 43. So in this case, if you run x is y, it will actually give you true. X is z also gives you true. And you can see that x and y actually have the same ID as well. And Python does this with any value of any immutable type. So here you can see the exact same thing. X is the word foo, y is the word foo. When you use is, they are equal. However, in this example, it doesn't. Good fun. Ice cream and ice cream. X is y? Nope. Why is that? Well, it turns out when Python does and doesn't take the shortcut is quite complicated, and it actually changes from one version of Python to the next. Behind the curtain a little bit, I did a take of this where I tried to do x is y right after running this code, and it actually gave me false here. And the reason it gave me false was because I had previously said that x and y were lists, and so it decided, oh, clearly these must refer to different things. And later on, when I reassigned them to make them 43, it kept that behavior and thus used different objects, and so I got a false result here. Kind of ridiculous. So when does Python take the shortcut? When does it not? It's kind of complicated. It's also possible, depending on your version of Python, it might be different. However, in terms of our code's behavior, we just need to be aware that this is a thing that can happen. So when you see that two variables just happen to have identity equality, you can be aware of this possibility. Later on, we'll see that most Python operators are implemented using functions. The fact that Python allows you to switch back and forth between, x could be 5 and then ice cream 2 seconds later is different from a lot of other languages. And alias, if you're, familiar with English, is something used when a person is known under a different name. So, Eric Blair's alias is George Orwell. They are two names, but they ultimately refer to the same object or person in this case.